All right, final section of the unit, section 4.6. This is a nice introduction to probability. I took a whole year of probability courses in college. I think it's fascinating, and I really can't wait to share just a small glimpse of it with you here. So we're going to start with permutations and combinations. Now, they sound similar, and even when we look at their definitions, they might seem similar, but they're actually two very different concepts. Both are looking at how we select objects from a collection. So if we have a whole group of things, how many ways are there of selecting like three of them? But they differ in one key way. For permutations, the order of the objects matters. So the order we're selecting them, the order we put them in matters. Combinations are less picky. Combinations are just concerned with the different groupings. So the order doesn't really matter as long as we're not counting different groups as the same. So let's consider a small group, just three letters, A, B, and C. How many ways can we select three letters from this group? From A, B, and C. If the order doesn't matter, so if we're looking at combinations, there's only one way to choose all three of them. One. Since order doesn't matter, A, B, and C is the same as B, A, and C, or B, C, and A, or C, B, and A, and so on. If order does matter, though, so if we're looking at permutations, then there are actually 6 ways to choose 3 letters from this group. And we've listed those 6 ways here: ABC, ACB, BAC, BCA, CAB, and CB and A. Now let's stop for a second. There was a collection of 3 objects, and the number of permutations of them was 6. So 3, we got 6 from it. We know that 3 factorial is 6. So is it true in general? And actually it is. The number of permutations of n objects is simply n factorial. Why? It's an excellent question. Well, let's think about it. So if I'm choosing 3 objects from this group of 3, then I have 3 slots, right? I can put A first, or B first, or C first. So that's 3 different choices to start with. And then for each of those 3 choices, I'm left with 2 choices for the second. And then after I've chosen the first and the third, I only have 1 choice left for my third slot. 3 times 2 times 1. So this is true for any group. So if I have 5 letters and I want to know how many different ways can I order them, that's 5 for the first one, times 4 for the second, times 3 choices for the third, times 2 times 1, which is just 5 factorial, or 120. All right? So find the number of ways, different ways, to place 4 unique books on a shelf. All right, well, I have 4 choices for the first slot, times 3 for the second, times 2 for the third, and then I'm left with whatever's left over for the last one. So that's just 4 factorial, which is 24. So take this a step further. So we just asked, how many different ways are there to place all 4 of my books on this shelf? But what if I only want to know the number of permutations of 2 books on that shelf? So I have 4 total, but I only want to permute 2 of them. So if we keep using the factorial, there's 4 factorial total, but that's too many permutations. I'm only choosing 2 books, right? So 4 times 3. I want to stop after that. I don't want to keep going. Because I choose my first book and then I choose my second from what's left. So that means I need to divide out the 2 times 1, just like I wrote down here. But 2 times 1 is 2 factorial. So really, I have 4 factorial over 2 factorial. So the answer to this is 24 over 2, which is 12 different ways. In general, then, for n objects, and I'm calculating the number of ways to order k of those n objects, then we have the following formula for permutations, and it is P of nk, or the number of permutations of k objects from a group of n, is n factorial over n minus k factorial. Just like we found up here. I have the total number of permutations for n objects, and then I'm dividing out by like where I want to stop. So I'm dividing out by, if I'm choosing k objects, the difference between n and k, n minus k factorial. Okay. Now from this formula, we can derive our formula for the number of combinations of k objects from a group of n. So we're starting the same way. We want the number of permutations, but since we no longer care about order, we have to divide out the groups that are the same. So in permutations, just like up here, we're counting different groupings differently because their order is different, but combinations don't care. Combinations are fine with A, B, and C, and A, C, and B being counted as the same. So P of nk is what we're starting with, and then we're dividing out by k factorial. We're dividing out by the groups that we counted more than once. And when we write that out, pnk, remember that was this, what we got up here, we end up with this final formula. Does this look familiar to us? N choose r equals n factorial over r factorial times n minus r factorial. In this case, we're using k instead of r, but it's the exact same formula. So really, we can use the binomial coefficient to find the number of combinations. Remember that we read n r, that really should be n choose r, as n choose r. And this is why. I have n objects and I'm choosing r of them. I want the number of ways I can choose r of them. That's where that weird sounding notation comes from, n choose r. So let's look at some actual examples of this. A baseball team has 15 players. How many 9-player batting orders are possible? So I actually pulled this example from the internet. I would have no idea how many players are actually on a baseball team, nor how many batting order. I don't even know what a batting order means. But order matters, batting orders. So order matters, that means we're looking for permutations. Order matters, so we want permutations. So I use my permutation formula, n factorial over n minus k factorial. This is n, this is k. N choose, well, it's not n choose r, because that's for combinations. So 15 factorial over 6 factorial. And we get 1,816,214,400 different possible batting orders on this baseball team. That's an insanely large number. Truly. But this is the formula. Now let's look at another interesting example. And for these kinds of questions, there are a lot of interesting examples we can use cards with. So how many possible 5-card poker hands are there? Well, does order matter? No, order doesn't matter. Because the order we draw our cards doesn't change which cards end up in our hand, right? I can draw 3 aces and 2 kings, and that's the same as drawing 2 kings and 3 aces afterwards. It ends up being the same poker hand. So we're using combinations. That means we're looking at n choose r. There are 55 cards in a standard deck, and I'm choosing 5 of them. So 52 choose 5. Plug into my formula. 52 factorial over 5 factorial times 52 minus 5 factorial. Plug that in to a calculator, 2,598,960 possible poker hands. That's a lot, but also maybe not quite as many as you might think. All right, permutations and combinations. Really important, really interesting. There's a lot of fun things we can do with it. And in fact, we're definitely going to go through some more fun examples in class. But for now, I also want to move on to some basic probability. Okay, so most of us are familiar with probability in a general sense. Probability is a number between 0 and 1, 0 being impossible, 1 being certain, that represents the likelihood of an outcome of an event. So for any experiment or for any event, we say that the sample space is the set of all possible outcomes for it. So I think it's more helpful to see some examples of what sample space means. So what is sample space? What is the sample space for a fair coin flip? Well, what are the possible outcomes of this event, of this coin flip? We could get heads, we could get tails. That's the sample space, heads or tails. There's no other possible outcome. What is the sample space for the roll of a fair six-sided die? I could roll 1, 2, 3, 4, 5, or 6. Again, there are no other possible outcomes. It must be one of these. Okay, so that's what we mean by sample space. Given a sample space, we say that the probability that an outcome A, whatever A is, occurs is P of A. So we'll say P is the probability. And we calculate it by taking the number of desirable outcomes, the number of outcomes A, over the total number of possible outcomes. So what do we mean by that? Well, consider flipping a coin. Okay, so the probability that it comes up heads is 1. Look at my sample space. There's one outcome that I want, heads, over the number of total outcomes, which would be heads or tails, 2. So that's why when you flip a coin, probability that it's heads is 1/2. Probability that it's tails is also 1/2. What is the probability that a 5 is rolled when rolling a fair six-sided die? Well, we wrote out the sample space up here. The number of outcomes that we want, 5, well, that's 1. There's one outcome that we want. Over the total number of outcomes, and there are 6 possible outcomes here. Total number of outcomes. And intuitively, that should make sense to us. There's a 1 in 6 chance of rolling any number with a fair six-sided die. Okay. What is the probability? Oh, I wrote that in the wrong spot. So sorry. 1 over 6. 1 is what we want. 6 is the total number of outcomes. Apologize again. Got a little ahead of myself. I'm so excited by probability. What is the probability that a 1 or a 6 is rolled when rolling a fair six-sided die? All right, well, the probability that I roll a 1, that's a 1 in 6 chance, as we just saw. And then the probability that I roll a 6 is also 1 in 6. So the probability that I roll one or the other means I just need to add them. It's 2 over 6, or 1/3. Or, like in the problem, or which means mutually exclusive events, events that can't happen together at the same time. I can't roll both a 1 and a 6 at the same time. I have to roll one or the other. Means I add the probabilities, just like I did here. I added them. What about something like a letter B? What is the probability that a 6 comes up twice in a row when rolling a fair 6-sided die? The probability that I roll a 6 first time is 1 over 6. And then the probability I roll it a second time is a 6. So I'm rolling a 6 and I'm rolling a 6 again. That means I multiply my probabilities. For independent events, or events whose outcomes do not affect one another, and means I multiply the probabilities. So here, these two dice rolls are independent events. A roll does not affect a later roll. And intuitively, this should make sense to us. We've known, I'm sure we all know this already, that if I flip a coin, the outcome does not affect the next coin flip that I do. If I roll a die, it doesn't affect what I will roll next, or 10 rolls from now. Each event is independent of one another. So for independent events, when I'm looking at multiple events taking place, I'm multiplying the probabilities. But what happens when those events are not independent? What if they're dependent on one another? Then there's another kind of probability that we need to talk about. The last thing that we're talking about this section, the last thing we're talking about this unit. So let's look at an example to understand what we mean by this. Suppose an urn is filled with 2 blue marbles and 3 red marbles. If marbles are drawn without replacement, what is the probability of drawing 2 blue marbles? Without replacement means that I'm drawing a marble and I'm not putting it back. I'm just keeping that one out and then I'm drawing another one. That means I'm changing the situation. I've drawn a marble, so I've changed the total number of marbles in my urn. These events are dependent on one another. One marble draw is affecting the next one. It's changing the probabilities of what comes next. That means that we need a special kind of probability, and we call this conditional probability. So here, the probability that a blue marble is drawn and then another blue marble is drawn, so what I want, equals the probability that I draw a blue marble, and so times the probability that a blue marble is drawn, given that I already drew a blue marble. So I know it's a lot of words, but let's think about it and think about what this is actually representing. So in general, for events A and B, the probability that A and B happen equals the probability that A happens times the probability that B happens given that A already happens. And then we have this straight up and down line that just means given that. Note that we also sometimes rearrange this and write it so that we're solving for that conditional probability, for the probability of B given A. That lets us solve for that conditional probability directly. And also note that when A and B are independent, the probability of B given A is just the probability of B, since they don't affect one another. So then we get the formula that we used up here. We're just multiplying the two probabilities. P of A times the P of B. But anyway, I digress, as I often do. Back to our current problem. We'll say A is the event that we draw a blue marble. Draw a blue marble. And B is the event that we draw another blue marble. So then the probability of A and B happening, or the probability that we draw 2 blue marbles without replacement, is the probability of A times the probability of B given A. So the probability of A, probability that I draw a blue marble, is what I want. There are 2 blue marbles in that urn. over the total number of outcomes. There are 5 total marbles. And that's P of A. P of B given A is times. Now we've changed the situation after that first event. I've taken out a blue marble. That means that there are 4 marbles left. And if I already drew a blue marble, there's 1 blue marble remaining, 1 in 4. Multiply these together, and I get 2 over 20, or 1 over 10, is the answer to my question. All right, one more example, and there are 2 different ways to solve this problem, and I'm going to go through both of them. One is more complicated than the other, but I want us to see it and think about how all of these things that we talk about connect. So we're going to look at the more basic probability approach first. What is the probability of drawing 2 aces from a standard deck of cards? All right. How many aces are there total? What do I want? There's 4 aces, and there's 52 cards total. That's for my first draw. For my second draw, I want another ace. So there's 3 left and 51 cards left in the deck. That's for my second draw. So multiply these 2 fractions together, simplify, I get 1 over 221. It's actually not bad odds that I draw 2 aces in a row. Kind of surprising, to me at least. So that's my answer, thinking about basic probability. Now we can also take a combinatorics approach. I took a whole class on combinatorics in college. Combinatorics, combinations is where it comes from. Different ways of combining things. So we're looking at our formula for combinations, n choose r, and there's a way we can solve this problem using our combinations formula. So just like all probability, this never changes. I have what I want over the total number of outcomes. So what I want is to draw 2 of the 4 aces. 4, choose 2. I want 2 of the 4 aces in the deck. The total number of outcomes is choosing 2 cards from the 52 total. What I want, drawing 2 aces from the 4 in the deck, over the total number of ways I could draw 2 cards from the deck of 52. 4 choose 2 over 52 choose 2. And if I calculate that, use my formula, simplify, I get 6 over 1326, which reduces to 1 over 221. All right. So hopefully I didn't confuse you. Whichever method that I just used makes more sense to you is totally fine. But I wanted to show that there are ways that we can connect these and solve these using other methods. All right. That's it for Unit 4. I feel like Unit 4 is it's a lot of interesting math. It's a lot of math that we don't usually get to talk about, and it's a lot of setting us up for new ways of thinking, new kinds of problem solving, which is really the whole point of math anyway, is to think and to problem solve. So write down questions, come to tutoring, please. I'm here almost every day. And let me know if you want to have a cool conversation about math. All right. Have a good one. Thank you so much.